get started. So first, I want to talk about the homework for a bit. So the first question was on a wage model. So this is sort of the first time where we've gotten into a data set whose size might cause could get into some limitations. So you can get data through the American Community Survey for public use microsample units, which you can aggregate up to states or counties or whatever. So we were just using 1 year in one state here, but it could already be a little bit of an issue in terms of the size of the data set, being able to do what you need to do. So that's why I suggested everyone pick a state that is considerably smaller in population than New York. But there's certainly a lot of analyses where you might want to look at all the states or more than 1 year and or more than 1 year. And then that can get into computational limitations. It can certainly take a while if you have to evaluate the log likelihood function over potentially millions of people. If you use like the 5%, this is like 5% or something. It excludes some smaller places for the 1 year sample. But anyway, 5% of the United States is going to be millions of people potentially that you might want to analyze, even if it was just 1 year. So Bayes' rule continues to work, still valid, as we saw much earlier in the semester. Bayes' rule is valid if you have one observation. It is valid one observation at a time, even if you're going up to the millions. But one of the things that people criticize about Bayes' rule is that it takes a long time, maybe a prohibitively long amount of time, when you have data sets whose log likelihood function takes more than milliseconds to evaluate. And if you have to do 4,000 iterations, and each of the iterations is going through like 10 leapfrog steps, and the log likelihood takes like a second to evaluate, well, you certainly could have hours of runtime, and that causes a lot of people to give up on learning Bayesian stuff, even though in the social sciences it's rare to have a prohibitively large data set for using Bayesian analysis. I mean, the census is about as big, census data is about as big as it gets. And 5% of the population is only in the millions. But there are certainly, Facebook, Google, any like huge tech company is going to be using internal data sets that could be much larger than that. And so that causes some people to abandon using Bayesian methods. It causes other people to look for Bayesian-ish methods that don't use MCMC. So can we evaluate the log likelihood function a much smaller number of times than what it takes to do STAN, etc. But I would say for social sciences, the amount of times that you have a data set where, well, one, social scientists tend not to have data sets that are truly huge. Two, social scientists have much less time pressure than what they think they have. I mean, if it takes you a month to run something that's not really a big deal in social science research. You just run it on some server and you wait until it's done, and then you send it off to be published. So whether it could finish like a week earlier doesn't really make a whole lot of difference. But there are situations, mostly outside of social science, where you have legitimate time budget that could be exceeded if you were using. So anyway, this is for Connecticut, which is a state, economically speaking, a lot like New York, but with a smaller population. And read in the data, select people who actually have positive amount of wages, and then get an indicator function for whether they're exceeding or equal to the maximum value, which is the top coded value. That exact number differs a little bit from state to state, but the top 1/10 of a percent or something in each state is being censored. So there's a lot of models that could be and have been estimated using these data. It's probably the most common data set for studying wages, or then at least start with this data set and maybe merge in some other stuff. And so there's like thousands of economic papers that even if you weren't already familiar with, you just like Google for one of them, you could probably come up with something. This one that I use is fairly simple. It goes back at least to someone named Mincer, who sort of started, I guess, human capital sort of literature. And the main predictors here are the amount of schooling that someone has and experience, which we're going to proxy with a quadratic function of age, as usual for me, rescaling age to be in units of decades. And then if you have this as a base function, you can add on some additional things, whether you're interested in discrimination or other things like that. So I put in an indicator for women. And then, if you just call model matrix, you can get the X matrix that would be used for a model like this and subtract the means in order to get mean deviated predictors. Allows you to interpret the intercept as the expectation of the logarithm of wages. So we're modeling log wages here using a normal distribution. But anyway, we can interpret the intercept relative to centered predictors, and this generative process is going to have a very similar structure to the survival model that we talked about last week. It's just we're using a normal likelihood here. I think we used exponential before in the survival model context, but hopefully you get some understanding by now that you can swap in with minor modifications different things in a generative process for a generalized linear model. Do things more creative than just normal priors, or do things for making generative process for outcomes that are in different sample spaces, etc. So this is going to be for something that has a maximum of C, and y that we observe is equal to the true wages if the wages are less than the top coding value C. We're going to use an exponential inverse link function, which is fine for this, but when we actually go to model it, instead of using an exponential inverse link function, we're going to model the logarithm of the outcome and use identity link function. Errors are normal. Everyone has standard deviation sigma. You can have some prior on that sigma. You've got a linear predictor depending on what your x's are, and then you have priors on the intercept, priors on the coefficients. So, you know, that, except for this truncation mechanism, is pretty much what we've been doing before. And, you know, including the truncation mechanism is not particularly difficult, either for the generative process or for estimating the model. If you're going to include polynomials, then honestly it's pretty rare to include high order polynomials, but the predictions can get pretty crazy unless the coefficient on the higher ordered thing is pretty small. So certainly want to have an expectation on the coefficient of squared age being, you know, close to 0, if not actually 0. Can have different standard deviations on different things here. Main thing for these models is to have something reasonable for a prior on the intercept expectation, in this case of the log wages, for someone whose predictors are average. And so if you think about what if you think about what wages would be for a person with average predictors, then the logarithm of that would be a starting point for a prior on the intercept, but should have some uncertainty around that. Again, in log units, so you draw from the priors and then cross join together the priors with the predictors in order to make eta. Puts your linear predictor there, draw the errors from a normal distribution, standard deviation sigma, create y star, which is sort of true wages, or under the model, true wages. And then, depending on whether that's greater than or c, we get, you know, the y that's observable. And then, you know, you can go to make predictions. So I guess the main thing here, when evaluating a prior predictive distribution, you want to put the wages in dollars, even if you put the scale in log units. So saying someone has like a log wage of 10 or 11 or something like that doesn't make a lot of sense to a lot of people intuitively, and thus it's hard to say whether like a log wage of 10 1/4 is that reasonable or not. The only way to figure out if it's reasonable is e to that, and then you're in dollars and make it bigger. But you might want to put the scale along the horizontal axis here in log units, and so basically these are equally spaced with, you know, changing the exponent by 2, anyway, something like that. So anyway, took a few different tries, but eventually got something that I thought looked reasonable. You know, it's going to have a median somewhere around there, a little bit of chopping off in the right hand part there, below 1 million. But, you know, that was something that I thought I could live with. And honestly, if you can live with it, it's already plenty good. When you have this many observations, hundreds of thousands or so, don't need to do too much obsessing about getting your priors or your prior predictive distribution exactly right, because it's easily going to be shifted if necessary, and to some extent it always is necessary, by the massive amount of data that you are conditioning. So if you had something that looked anything like this, I think that would be fun. One thing that wasn't really asked, but we need to reiterate it, a lot of people in the social sciences would look at something like this, or empirical version of something like this from like the actual wages or whatever in the data set, and would say, well, that doesn't look like a normal distribution, therefore normal likelihood is inappropriate. And while it is true that that is not looking like a normal distribution, that does not contravene the assumptions of the data generating process. So here was a data generating process where we explicitly assumed the errors were normal, which is what the model assumed. And yet we get an observed distribution of or observable distribution of the predictions that's not normal. So clearly it's not required for the outcome, if you did like a kernel density plot of the outcome to look normal, that's not a requirement of the model. So what makes people confused? Well, one, the assumption of normality is about the errors, not about the outcome. If we didn't have predictors, if we just had an intercept, then that would essentially be the same. So what is actually being assumed here, everybody has different levels of schooling and ages and whatever, is that each person has a normally distributed outcome, not that it's the same normal distribution for everyone. So the expectation of everyone's normal distribution is different, which is sufficient to cause the predictions to not look normal when you pull them all together. Secondarily, even though we've assumed the errors to be normal, that's conditional on sigma. But sigma has a prior, in this case, an exponential prior. So if we marginalize over sigma, the marginal distribution of the errors is going to be more heavy-tailed than a normal because we have additional variability coming in because we're not certain as to what sigma is under the prior. So both of those are sufficient to cause the predictions to not be normal. And in addition, we have a non-symmetric inverse link function essentially being put in where we do e to the something. So for all of those reasons, this is not supposed to look normal. But this embodies the assumptions that we made in the data generating process. Now those assumptions can be wrong, but they're not wrong just because this doesn't look normal. Questions about that? All right. So then, you can use the same priors that you use to generate the predictions. Use BRM with the censoring indicator to do this. Get back results. And then one of the things that you can do is, with that object, is test hypothesis about the coefficients. Again, this is not testing a null hypothesis. This is not testing a point hypothesis. This is testing what might be thought of as a research hypothesis, what it is you're attempting to show with research. And if you were interested in showing discrimination, well, kind of a necessary condition for that would be to show that because of gender, because of race, because of being not a citizen, something like that, your expected log wages and hence your expected wages lower than the reference group. And so in this case, unsurprising, particularly with this amount of data, that we get an estimate of the coefficient on women to have a mean of -0.44 with a 90% credible interval between -0.7 and -0.42. None of those 4,000 or whatever draws were positive, and so we get a posterior probability that the coefficient on female is negative, as being essentially 1. Or if you want to be technical about it, less than 1 in 4,000. But in any event, extraordinarily small, and so that would, go part way to establishing discrimination research, something like that. But you could have tested other hypotheses about coefficients. All right. Then if we look at the posterior predictive distribution, in particular if we look at the posterior predictive distribution of the average wage. So again, you want to EXP the predictions because the predictions are in log units. So you want to anti-log that, put it into dollars before analyzing it or before taking the average. So we're interested in the average wage in dollars, not the average log wage. And then we get something like this, posterior distribution of the average wage. You know, we're fairly sure it's between 90,000 and 100,000. But that is substantially larger than the average that we observe in the data. And that is because although the number of people who are top coded in Connecticut is a small percentage of people who earn wages in Connecticut, those people's wages are huge. And having a small number of people with truly huge wages is enough to shift the average over by $10,000, $15,000 if you include in the average, you know, people who are earning like millions and millions and millions when the highest allowable value in the data is like $750,000. So if you were interested in anything having to do with average or inequality or variance, all of those things are particularly sensitive to extreme values, and top coding makes all that less extreme. And so you really need to model the underlying Y star in order to make, you know, any sort of an intelligible argument about inequality or things like that, or inequality at least that's sensitive to the top. If you're talking about inequality of the bottom relative to the median, that might be a somewhat different story. It's, I think, worth noting that. And if you do the model comparison, it actually can come out maybe what you wouldn't expect. So a model that just ignores the censoring, we're actually expected to predict future log wages better than a model that incorporates the censoring. And that is, in this, I don't think that's a generally true statement, but in this case, top coding is relatively rare. And so if you're, let's say it was like 0.1% gets top coded. And so if you're interested in predicting wages, well, if, you know, 0.1% or something is top coded, that's maybe not worth the trouble if you're thinking about your ability to predict accurately 99.9% of the wage earners, even if you're not so accurate on the very top. So that's a limitation of using expected log predicted density to choose between models. And it's an important limitation. So expected log predicted density, the only thing in your utility function is how well it predicts. If you're interested in any other things, then that would not be reflected in the ELPD. And so if you're interested in saying something about inequality of wages, well, it may result in predicting worse because you're estimating like a more complicated model, but you can't just ignore the fact that there's lots, or not lots in percentage terms, but enough extraordinarily high wage earners in Connecticut to throw off, pretty much every aggregate measure if you didn't take that into consideration. So, predictive ability is not the only criterion that you might want to use to choose among models. However, it is the only criterion that supervised learners use to choose among models. And so, to the extent we want to come up with something that's not only comparable, but just flatly way better than what supervised learning does, well, you're going to have to live with the limitations of that, even though the limitations of the things that supervised learners use is much worse, more severe, and just wrong a lot of times. So any other questions about this wage thing? Something that is reasonably common. Yeah.
Sorry. Is it common to not get zeros for both? Because even when I did it, I was kind of questioning myself.
This?
Yeah, both zeros. Yeah.
Well, for when you do Lu compare, the best model is always going to have zeros for both because it's comparing with itself.
Oh, okay, got it. Oh. Okay.
Right. So ELPD is only meaningful across models, and so this is to say, the one with taking into account the censoring is negative 210 worse in terms of its expected ability to predict future data. But if we did the no censoring model, we would be way, way off if we were talking about any aggregate feature of the population. And so those are especially important things to worry about when you have these things in the social sciences, which sometimes we do, that are very skewed. Income, obviously, wealth, even more so. If you're talking about sizes of firms or anything like that, you can definitely get into this hugely skewed thing. And to some extent, that gets lost if you only think about the outcome as being logarithm of something that's hugely skewed, because logarithm takes away a lot of the skew. But you really need the Bayesian approach to reverse those transformations when you're talking about the predictions at the end, because you still get back a distribution of the thing that you're interested in, as opposed to just a point there. Okay, so second question about this survey New York Federal Reserve does regularly about inflation expectations. So you'll see this data set referred to, maybe not by name, but you'll see it referred to a lot in media articles, both because inflation expectations play an important role in a lot of theoretical models in economics, but also are thought to be influencing the approval of Joe Biden, or lack thereof, and chances for his re-election. And that gets to, one of the things that you'll see in the media these days is, well, the economic data over the past year or two has been pretty good, but people's perception or people's stated perception of the economy has been considerably worse than what the data have been. And so that might lead you to think about, is there some modification to Fair's model that we talked about on the midterm, it has that like inflation thing in it. So, you know, what if you replaced actual inflation with what voters believe inflation to be? That might yield better predictions for how those voters are going to vote if they think, you know, inflation has been or will be twice as bad as it actually has been. So this has and probably will continue to get some attention played to it as we get closer to the election, and that raises certainly the issue of, well, who and maybe why are the people who are perceiving inflation to be or anticipating inflation to be over the next few months, you know, so much higher than what like the Federal Reserve is anticipating. So we load up the data. This data set has, it's not atypical, but they ask the questions to the same people like 6 times or something like that in consecutive months. So they don't re-ask the person like how old they are. They just sort of ask that once. And so we'll just keep here the first time the person answers the question, but it results in people from like 2020 up to the current being included in the data set. And the variable names here are pretty awful. They just sort of refer to which question number it was. So you may have to do quite a bit of wrangling to get this into a format where you could, you know, specify a model for something like this, and you know, remember that, you know, or not have to remember that Q35_1 is the variable that indicates the person is white, or you know, whatever it may be. Okay, so we got that. Again, I put age in decades and then excluded people who said their age was less than 18, which, if it were true, means they're not eligible for the survey, and people who put like 400 for their age, which is not biologically possible. So anyway, generative process for this was laid out in the text of the question. So we have observed inflation percentage anticipated over the next year to be sum of eta and the error term. That's the same as we've done before. Only thing that's really different from what we've done before is now we're having a epsilon that is taken from a normal distribution, but rather than saying that normal distribution has expectation of 0 and a standard deviation of sigma for all people, we're saying person n, the error is drawn from a normal distribution with expectation of 0 and standard deviation equal to sigma divided by the square root of tau n. So the nth person has their own error variance, which in the language of conventional frequentist econometrics would say this is a heteroscedastic data generating process. Here, we're not particularly modeling why some people have much more variability in their responses than other people. We're just saying the denominator here, or the denominator squared, is our beliefs about that are distributed gamma with shape and rate equal to nu over 2. Could generalize that, but if you do stick with this form, then you can get some analytical results that otherwise wouldn't be possible. So basically we're saying the denominator here is a random variable about which we have beliefs, so it's got to be positive, but could be extraordinarily close to 0, in which case the error variance for the nth person can be rather large. And even though we're not exactly modeling in this case why some people have bigger error variances than other people, it's not hard to think of reasons why that might be the case. So maybe some people don't understand what the definition of inflation is, and other people do. And so the people who don't understand what the definition of inflation is are likely to have wildly varying anticipations of what inflation will be when they don't even understand it. Or you have people who, like, their way of thinking about inflation is just the price of gasoline, which, you know, can vary a lot. Or gasoline and food. So the price of gasoline and food vary a lot. But ignoring the price of renting an apartment, which doesn't change that rapidly, ignoring the price of like flat screen TVs, which have gone like pretty much straight down for a long amount of time. So if you don't really consider prices of everything, you just think about gasoline and food or something like that, then that is going to have more variability than someone who thinks about prices for, you know, everything in the market. So for whatever reason, we might think that there is heteroscedasticity in the error variance. And so we need to have prior distribution on tau n. In this case, it depends on nu. We need to have a prior distribution on nu. But from there, the rest of it is the same as what we've seen before. And so we get a linear predictor. We can predict from it. In this case, we got a lot of predictors. So I do this thing. You've seen it before. To quickly multiply together coefficients and variables. So if you did this, that'd be totally fine. And so draw tau from a gamma distribution and then draw the Gaussian errors with standard deviation sigma divided by the square root of tau. But both sigma and tau are random variables. So marginally, the errors are going to be more heavy-tailed, even though they come conditional from a normal distribution. So if we go to plot that, that's the one in black here. You can see it's literally the same density as the one in red, where the one in red I did by, instead of drawing tau, drawing epsilon from a t distribution with new degrees of freedom and scale sigma. And as I alluded to in the text of the problem, if this is your data generating process that you assume, and you analytically integrate out all the taus, what you're left with is a marginal distribution for the errors that is student t with new degrees of freedom and a scale of sigma. And so that yields an equivalent prior predictive density if you do homoscedastic errors from a t distribution or heteroscedastic errors from a normal distribution. So, like I said, making these particular assumptions allows you to integrate out the taus from the posterior distribution. Now, when you're simulating from the prior, I would recommend you do whatever is kind of the easiest for you to understand. So if it says this, you know, do that. But when you're drawing from the posterior distribution, well, if we had to estimate a tau for each person, and there's like thousands of people in the data set, we would need to be estimating thousands more parameters. Now, Stan can do that. Take a little while longer. might be more sensitive to some of the tuning settings and stuff like that. Stan can do that. But if you can analytically integrate out some stuff that you don't really care about anyway, then you should. And in this case, you can. So the right way to, or a right way that's much faster when you call BRM is to use student T likelihood, estimate sigma, estimate the degrees of freedom, rather than normal likelihood and estimate all the taus. As we saw in this plot, those are in a meaningful sense equivalent. Your beliefs about the outcome are the same either way you do it. But in terms of the amount of time and difficulty it takes to draw from a posterior distribution, it's much easier to draw from the posterior distribution that doesn't have the taus. So marginalize over them, estimate your coefficients, estimate your degrees of freedom, estimate your sigma. Does everybody understand? I think we hadn't really seen that before exactly. And so it might have been a little bit of something that was difficult to get your head around on this homework. Actually, we have with like beta binomial, but that was with a totally different outcome, so you might not have seen the connection. So let's say, you have a bunch of success probabilities, but, they have a beta distribution, and you integrate that out, and you integrate the success probabilities out, and you're left with the beta binomial. Similar deal here. Integrate out the taus. You're left with something similar, but you haven't changed your assumptions. You've just made it easier to draw from this posterior distribution, which is rather easy. And you can look at the plot of any of the parameters, in particular for this one for nu, where it is rather clear that the posterior distribution for nu is rather concentrated, very close to 1. And 1 is actually the minimum value, even though theoretically it could be between 1 and 0, but the way brms estimates it, the smallest value of this is 1. Anyway, so student T distribution with 1 degree of freedom is a Cauchy distribution. And a Cauchy distribution is so heavy-tailed that it doesn't even have an expectation. The median is 0. It's so heavy-tailed, the expectation doesn't exist. So in this model, the expectation of the errors in the posterior distribution sort of barely exists. But pretty much any value of epsilon is consistent with the data. So that might be a fairly shocking result. There's not a lot of things in the social sciences that have errors this heavy, tails to the errors this heavy. And you might say, well, okay, is it particularly sensitive to any one observation where somebody might have put in that they think inflation over the next, year will be negative 100% or something ridiculous like that? As it turns out, no. Or at least for the model that I estimated, yours may have been a bit different, but I think for the most part, if you use that heavy-tailed error distribution, then the posterior distribution is not that sensitive to any one observation, because no matter how crazy an observation might be, it's compatible with the Cauchy because it has this very heavy tails, can never have expectation. So that, at least for me, was not a serious issue. And if the Pareto case are fine, then you can use leave one out concepts to, estimate R squared. So if we left out an observation, use the rest of them. To predict the nth observation, how well will we do? And the answer to that question is absolutely terrible. Lu R squared is actually estimated to be negative, which okay, let's just call it 0. So this model with like all the usual demographic stuff, plus like what region do you live in, plus the date of like the month that you took the survey or whatever, has no ability at all to predict someone's expected inflation over the next 12 months. And that can also be verified by, looking at, a Lu intervals plot. You can barely see the blue here because there's so many dots, but you can already see, even if I trim the vertical axis to be between like -10 and 100, so many dots outside the 90% predictive interval. So this model is not fitting well at all. Tremendous underfitting rather than overfitting. But that happens sometimes. Particularly happens with this. And so it's worth thinking about, even though I didn't put a question with that vein on the homework. Well, if inflation expectations is an important concept in macroeconomics, where like inflation can become self-fulfilling, in a manner of speaking, if inflation expectations are so important to an incumbent president's chances of re-elections, and if it is true that we can't explain why some people have high inflation expectations, other people have low inflation expectations, with anything of the usual suspects for predictors in the social sciences, well, what implications would you think that has for our understanding or lack thereof of social science?
That's kind of hard to say though. Inflation is kind of like, let's say in each topic, but just such a specific topic within itself, it's incredibly hard to predict. So, kind of hard to say.
Yeah, I think there's maybe a lot of things that can be said for this, but if we focus specifically on this like self-fulfilling prophecy aspect of economic models, these assume extreme level of rationality, or it's not even extreme, they just assume that people are rational, and kind of at a minimum their forecasts for inflation are like, kind of right on average. And so if they anticipate 10% inflation, then they're gonna ask their boss for a 10% raise, and if they get a 10% raise, then you're more likely to get the 10% inflation, and it can kind of spiral out into that sort of thing. But if we have no ability to say who thinks inflation is going to be large, who thinks it's going to be small, no ability to explain that variation, and what people say doesn't seem to be systematically related to anything that would make sense. So like maybe prices in the Northeast are rising more rapidly than prices in the South or whatever, and we would anticipate the South dummy variable to show up on this, but it actually pretty much doesn't. But if we can't really anchor what people say to anything that makes sense. That sort of undermines the case for people having a like somewhat rational forecast for what inflation is. In addition, if you look in the data, there are some people who are say negative 100%, or some people who say 10,000%, and it's difficult to know whether those people were just like breezing through the survey in order to get to the end as fast as possible and collect their $20, or whether we're dealing with a genuine idiot from the population, or someone who just like does not understand what inflation is and thinks that 10,000 is a plausible value for the United States, when it's like, I mean, this happened in Venezuela and some African countries sometimes, but never for a developed country that has an independent central bank. Things like that. Inflation was considered to be high in 2022 or whatever, when it was like 10. So that's obviously orders of magnitude less. So it also raises the issue. So what we don't have in here is anything concerning partisanship or where you get your news from. Those questions not asked in these particular survey, but other surveys, consumer sentiment and whatnot, have documented a tremendous amount of disconnect and polarization based on, if you watch MSNBC versus if you watch Fox News, in terms of your anticipation of inflation. So
I know there's a variable called numerical literacy, but at least a variable on how well versed they are in economics. So
yeah.
Account for
So could it include? Did you include that stuff?
numerical literacy.
Yeah, or
Yeah.
lack thereof.
Yeah.
And did that make much of a difference?
I gotta go back and look, but I don't think it did.
I mean, certainly people did real badly on those questions. I do know that. As to whether it correlates with their inflation expectation, I don't think it's super strong. But again, it could be the people who think 10,000% inflation are just real bad at math.
Or maybe just putting down some snarky answer.
Right, or, partisan answer. So partisanship and lack of math ability is a dangerous combination. All right, so last question. Thought it was kind of interesting. So who all was persuaded by the author's argument that model weights in like a neural network model should not be considered speech as, the courts interpret it for First Amendment purposes? So you have just like a list of numbers, weights for a neural network or a random forest type deal. The author argues that those would not or should not be considered speech, and thus might be subject to export controls and things like that. So who thought that was like a persuasive argument as applied to supervised learning stuff? Yeah.
I did. There's one part of his argument. Maybe probably a major, like a very small detail, but I agree when he said that because they are instructions to machines. But I like the premise I said, because speech involves the communication between two different people. I mean, I don't know. Somebody praying is communicating with maybe higher power within themselves,
or their laptop.
But I mean, I did agree that like if it's just rudimentary random instructions, then yes, but maybe for a bad reason, more of utility. Like, is there really a particular purpose of protecting that type of speech when it's just going to be random numbers generated for trying to optimize certain weights? So that part, yeah, but again, his premise that communications between two people kind of hurts me a little.
Yeah, I think that is certainly something that the courts are going to have to wrestle with. So in the 1700s, you know, the people who came up with the Bill of Rights or whatever, when they were thinking about free speech and expression or whatever, they were thinking about between humans. They certainly weren't thinking of, well, I mean, there's also the part in the First Amendment about religion or whatever, but they were certainly not contemplating communication or between a person and a machine, or communication between machines, or communication between like a person and their horse or whatever. Like, that's not what they were thinking about. But you know, we are already at the point where that might very well become, you know, an issue. And the rise of AI and stuff like that has already created a bunch of challenges for the courts that weren't, you know, anticipated when the Constitution and the laws and stuff were first written down, in terms of ownership of training data and, you know, all kinds of things like that. Other thoughts about the main premise of the article? Did you want to add?
Yeah, I put like, in addition, that like there is no meaning behind the weights, so it's only an instruction. I think that's like the main argument behind it.
Yeah, so I'd agree with there's no meaning behind the weights. I actually thought it was a little odd of his phrasing that the weights were instructions, when I would have phrased it, the code gives instruction to the computer to multiply the predictor by the weight, then push it in the activation function, take the activation function to the next level, like do the weights at that level or whatever. So I didn't exactly agree with, okay, this number, like 0.12345, is an instruction, when like the actual instruction is multiply that number by something else. But I don't know that totally changed his main point, that, you know, the numbers 0.1234, or much less a big list of those numbers, is not intended for communication between two people. Did you want to add something about the...
No, I didn't get that.
Oh, you got it? Okay. So, I didn't specifically ask this, but I think it's worth thinking about. So, would the predictions from a neural network model, as opposed to the weights that filter through the whole thing and yield the predictions, like the final prediction of, you know, whatever the neural network is predicting in the units of the outcome variable, do you think that would be a better candidate for speech than the model weights that generated the prediction?
I mean, I know you asked this question for number 2, but wouldn't that still kind of fall in the same lines of asking if like a posterior distribution should be, you know,
Well,
protected
that
against-
would be,
Is
yeah,
it
so
still-
he doesn't unfortunately explicitly consider a posterior distribution or a posterior predictive distribution. But even before we get to that, just in like machine learning neural network thing, I train a neural network to predict the stock market or something like that. And then I say my prediction for the stock market tomorrow or whenever it is going to be, you know, up 2%. Is the prediction that the stock market is going to be up by this or that amount a better candidate for, or a more, something that should be covered by the First Amendment, as opposed to a big list of numbers that would combine with the predictors and the activation functions and the neural network yielded that prediction. So the final output thing, rather than this intermediate stuff of the weights. Would that be something that you consider speech?
I would, because I mean, this is kind of going along my reasoning for the third question. But I mean, if it has the ability to be interpreted, to derive meaning from it, and actually take action on it, kind of like how we, you know, with our posterior distribution for our Pfizer vaccines, then I think it should. You know, even if, I don't know, thinking along the lines too, if like certain
Yeah.
symbols are protected, even though they're not actually speech itself, it's still something kind of mundane that we can ascribe meaning to, so I would kind of say maybe it falls along those lines. Not equivalent, but
Yeah, so I mean, predictions of an outcome is certainly something that humans might want to communicate about. And, you're just putting kind of specific numbers to your predictions when you do it off of or point predictions when you do it off of a neural network. So I thought it was a little bit odd that the author didn't address the question of whether the predictions of a model, how that would fall in relation to the first one. I also thought it's a little bit odd that the author didn't do what I thought might be the most obvious question to consider. There's a lot of stuff in the natural language processing literature about representing words with long vectors. So apple or whatever. There's a vector that you can estimate with neural networks, these sort of stuff, and you get like 100 double precision, or you can be greater than 100 size vector, like double precision numbers, and those represent the concept of apple. And then you can see the cosine similarity between the vector for apple and the vector for orange. And they're like correlated at 0.82 and stuff like that. So you can do analysis on language if you represent words as vectors and then apply linear algebra to the vectors. And so I think a fairly obvious question that the author didn't address is the vector representation of a word speech? I mean, clearly you could have English words like I like apples or something, which would be covered by free speech, whatever. But if you use the vector representation of the words in that sentence, does that make it not speech? As the First Amendment goes. But anyway, it doesn't address that question, so maybe we don't go too deep into it. But I think that's another question that courts are going to have to address if they address the question that is actually talked about in this article. So, second question, what do you think the author would say about draws from a posterior distribution? Would that, in his mind, be similar to a big list of model weights? Or do you think there's something about his argument that would make a distinction between model weights from like a neural network versus draws from a posterior distribution?
I said that I think it would be a relatively similar concept, because when you're doing a posterior draw, you're kind of getting, like, you're making an inference, right, with like the data that you get from your prior and the data, and that's kind of the similar thing with what the model weights are doing. It's, again, going back to the point where it's like, it's giving you the data, you're not like doing any like opinion or like thoughts or perspectives, it's just like simple mere constructions.
It's certainly a big list of numbers. I think that's probably what he would gravitate to. That if you're just like staring at them, you wouldn't know what to do with them on their own. It's sort of only useful in the context of the rest of the model, whose source code may very well be covered by the First Amendment. But I think it's reasonable to guess that he would make the same argument about posterior draws as he does about machine learning weights, particularly if he doesn't have any experience with Bayesian stuff, which there's no indication that he did. And since he's a law professor, I'm just going to assume that he doesn't. So anybody had any other thoughts about the second part?
There was a quote by him where he says, "There may also be rare situations in which the distribution of model weights is protected not primarily to enable others to run machine learning models, but rather because the act of the distribution itself expresses some other protected message." So I thought maybe if you go off that line of reasoning, he would maybe say that posterior distribution would be protected under speech because it has the ability to convey some sort of message. I mean, protected or not, I don't know, but that was kind of my line of reasoning for it as to why he might be swayed if he had some knowledge of Bayesian statistics.
Yeah, so I wish he'd gotten into it more explicitly. My guess is he just has no idea about Bayesian stuff and he wouldn't really be in a position to say one way or another, but I think from the bulk of what he was saying as opposed to like quoting a court or somebody else, I think he would say, okay, this is a big list of numbers. It's just functional rather than expressive. But then that raises the third and most important question is, do you agree with that? Or is there something about draws from a posterior distribution that should distinguish them from weights in a neural network model? What do people think about that?
So I said that it should be like protected by the First Amendment because you have your prior beliefs and then you have like you change your beliefs giving the data. So that's like kind of technically a conversational. It could be an argument for something. So you could say that it's technically speech, like data with prior beliefs and changing your prior beliefs to the posterior beliefs is like.
So I definitely think that if the courts were to interpret posterior distributions as the researcher's beliefs about something, then it would be extraordinarily difficult to say it falls outside the First Amendment because, like, if you say, okay, my beliefs about this or that have this sort of posterior distribution, how is that fundamentally difficult from saying, you know, my beliefs about religion or my beliefs about abortion or my beliefs about what the United States should do about the Middle East, all sorts of things that are really at the core of what we're talking about when we talk about the right to free speech and free expression. You're expressing your beliefs about some unknown thing. Whereas in a machine learning context, it doesn't yield beliefs because it doesn't yield a probability distribution. It does yield point predictions, and I think point predictions is sort of a gray area, but a point prediction is not a belief. It's not a distribution of beliefs. So I think that gets to the core of it, and Bayesians certainly think that these prior distributions, these posterior distributions, are expressions of belief. Moreover, I think it could be argued that, okay, suppose we have natural conjugacy or whatever, we have an analytical posterior distribution, and you say with the Pfizer thing, okay, my posterior beliefs about theta are distributed beta with alpha star and beta star as, you know, the shape parameters. And so we're not even talking about draws, we're just saying my posterior beliefs about theta are distributed according to this beta distribution. So like the mathematical statement. And if instead of having like analytical posterior distribution, you just have draws from that posterior distribution and you could plot them and say like the shape of my posterior distribution looks like this. Is there any real difference in the expressiveness of your beliefs as to whether you have like analytical posterior distribution that you could work out with a pen versus pencil versus a bunch of draws from that same distribution? Kind of the main premise of MCMC is that we can be as expressive about the posterior distribution with a bunch of draws as we could be if we could do it analytically, which in most cases we can't. So we have to use draws, but that doesn't really compromise our ability to express our beliefs about stuff. And so, yeah, I think certainly Bayesians would argue that draws or posterior distributions more generally are speech, reflection, expressions of belief. I don't know if the author would agree with that, but certainly Bayesians, I think, almost universally would. But you can certainly have Bayesian posterior distributions and models and stuff like that that are not particularly interpretable, or not like every aspect of it might not be super interpretable. So it seems like it's going to be a difficult challenge for the courts, and the courts are notoriously, bad at math, to figure this out. If it's sort of saying, well, if the model is sufficiently interpretable, then it's speech, and if it's sufficiently uninterpretable, then it's functional. Like, where's the line between interpretable, readily interpretable, and not interpretable? It's going to be a tough issue. Does anybody else have any more thoughts about that? All right. Okay, so for the rest of the day, we're going to be talking about ordinal variables. Again, we're going to be thinking about this in terms of the brms package. So although this applies to me, I still had almost nothing to do with the brms package. And one of the data sets we're going to consider is this one that we already have talked about, week 9. This polling data we had by Google from like the day before the 2012 election. And it has a bunch of variables in addition to saying who the person wants to win. And one of the things that makes the social sciences different from a lot of other fields is we tend to have a lot of ordinal measured variables. And so we need to have methods to deal with them. Age and income in this are already coded as ordered factors, which seems sort of reasonable. But by the same token, you can think about urban density as being ordinal, as well as 3 levels: rural, suburban, and urban. So you can think of those as being like degree of urbanicity that is being represented by a factor. And so in many situations, you don't have to, but you might very well want to assume that the effect of an ordinal variable on the linear predictor is monotonic. So if you think about like a logit model or something like this, if you had their income exactly, you might very well put that into a logit model, not merely as monotonic, but linear. Like that would be extraordinarily common if you observe their exact income number. But if you observe only their income category, but you think the underlying income is affecting their preferences for Obama versus Romney, then certainly you would think the effective income on the log odds of favoring Obama would be, monotonically related to income. And in particular, you might feel like the richer someone is, the more likely they would be to favor Romney, who used to run Bain Capital, versus Obama, who did not. So to understand that, we need to introduce a new distribution for us, known as Dirichlet. And a Dirichlet distribution is over the parameter space of probability mass functions. So it's a distribution over probability mass functions. So the parameters to it are non-negative and sum to 1. And the Dirichlet PDF has this form here. So this is a distribution over these vectors of size k that are non-negative and sum to 1. And they have additional parameters alpha that are non-negative. So the beta distribution, special case where k is 2, and then Dirichlet is a generalization to k greater than or equal to 2. We can come up with the mean and the mode of this distribution, and in particular, if all the alphas are 1, then we're raising this to the power of 0, in which case this becomes constant over the parameter space we're talking about, which is said to be the parameter space of simplexes, non-negative vectors that sum of size k that sum to 1. Also, important fact, if pi has a Dirichlet distribution, the cumulative sum of the pi's is going to be an increasing function. That's due to positivity and cumulativeness. So, model for the Obama-Romney 2012 election in mathematician using a monotonic construction for like one of the predictors. So the number of people who support Obama is binomial with some CDF for the inverse link function. Let's just say F is the logistic CDF to be concrete about it. Linear predictor, same as we've done before. Have an intercept, perhaps. And now we're going to do something a little bit different with the betas on this monotonic predictor. We're going to say we've got a cumulative sum going on the pi's, and then the whole thing is scaled up by lambda and divided by k being the total number of categories. In my ordinal predictor, okay, what's pi, what's lambda? Well, pi is going to be distributed Dirichlet, distribution on the previous slide, with some shape parameters a, which you might think by default could all be set to 1 to give you the constant density over the simplexes. And then we can put whatever prior we want, such as normal, on lambda. So because we have, these are all positive, and we have a cumulative sum here, this thing is going to be positive. And so the sign of the betas is going to be controlled by the sign of lambda. So if lambda is positive, then all the betas are going to be positive, but they're going to be in increasing order. If lambda were negative, then the betas are all going to be negative, but they're going to be in the other decreasing order. And if lambda were exactly 0, then none of the betas are going to make any difference. They're all going to be 0, but that's a special case. Yeah.
So lambda's just there to serve, just change the direction of the rate.
And the magnitude, yeah. So if lambda is really big, then we're going to have the really steep increase. If lambda is close to 0, we're going to have just like barely increasing.
But isn't it going to increase or decrease? Is it a different level of pi though if you're sampling it from a Dirichlet? How do you say it?
Okay, so when Dirichlet was little, his family moved from Belgium to Germany, and so he grew up pronouncing his name more German, but he actually his family came from Belgium. So you can either do it with like a French or a German.
Is that gonna be on the final?
No. But it did show up in my course evaluations one year. Like somebody wrote that my German pronunciation was terrible. I was just like, God. Of all the things you could complain about, you complain about my German accent from someone who's from Texas. Yeah, so anyway, you were going to say something about Dirichlet distribution.
The Dirichlet, doesn't that serve as part, it's like model partial effects? Because at least that's how McEarl talked about it in the textbook.
Yeah, same deal. Yeah, consistent with what McElroy said.
Okay, because he didn't have the lambda divided by k term.
Oh, he didn't have the k. Yeah, so the k just makes it like average.
Oh, okay.
But you could ignore the k realistically and just make lambda be bigger, whatever. That doesn't affect much. So the way in which we would draw this from the prior distribution, so Dirichlet, it's in Stan, but it doesn't come with R. There's another package that provides it, but if you wanted to draw from a Dirichlet, you can draw from a bunch of gammas and then divide by the sum. So anyway, do this. You get beta 1, which is just pi 1 divided by 3 times lambda. And then you have the sum of the first two divided by 3 multiplied by lambda. And then the pi's add up to 1, so your third one is just multiplying by 1, multiplied by lambda, divided by 3. Now you get prior draws of beta 1, beta 2, beta 3, along with gamma. And then the question of how you draw predictions then becomes similar to what we've done before, deeming the variables, cross-join the prior distribution with the predictors, and you just have, beta 1 times the dummy variable for rural, dummy variable centered for rural, beta 2 times the dummy variable centered for suburban, beta 3 times the dummy variable centered for urban. And beta 1, beta 2, beta 3 are going to have either an increasing or a decreasing relationship to them, depending on what the realization of lambda was. So 8 is your log odds, map that to probability by putting it into the logistic CDF, and then draw from a binomial distribution of appropriate size. We can then look at the predictions, which unsurprisingly, based on the priors that we give, probability of supporting Obama higher in urban areas, lower in rural areas under our prior, and then we condition on the data, see what happens. So, as usual, we can call the get prior to see what everything's called. So the default prior on the pi's is going to be Dirichlet with all the A's 1, so constant density under the prior for all simplicities of size, whatever. This mo age, mo income, mo urban density, those are the things we've been calling lambda. So the scale and directional factor on the monotonic thing. Region, we don't put the monotonic restriction on, even though possibly we could. But there's no necessary relationship between regions that we could order. Also, these binary variables, there's no need to put ordering on. If it just has 2 levels, then you just multiply the coefficient, I think. But anyway, don't use the default priors because they're terrible in this context. Well, these ones are not so bad, but the one on the intercept and the improper prior on the coefficients, those are. So, you can put some substantive priors on that sort of thing, call BRM, condition on the data, get back the plots. And so here we see, in particular, the lambda for age is fairly precisely estimated and definitely negative. So we're sure the older you are, the less likely you are to support Obama, more likely to support Obama. Some of the other ones were not as clear. So income, the lambda of that is not as precisely estimated, more likely to be negative than positive. So the richer you are, more likely to support Romney, probably, but there's a good chance that the sign is reversed. So we can look at those. These are the ones for like the pi's, and so they're going to be between 0 and 1. What's not clear from here, but what's true under the model, is that the pi's sum to 1 within their category. So we got that. If we visualize the posterior distribution of like the expectation for the 3 levels of urban density, unsurprisingly, we see the positive relationship, the same one that we thought in the prior, supported by the data. So you can do these sorts of things, don't have to, but it's an option. And it's a pretty good option, I think, for a lot of things in the social sciences. Basically, anytime you're like, well, I have this kind of crudely measured thing like rural suburban density that's actually just sort of a coarse measurement of an underlying continuous thing like population density, if I had the underlying continuous thing, would I say that has a monotonic or even a linear relationship? If so, then you should probably be using the monotonic constraint, even when you have to make it into dummy variables, because that's how it's measured in your survey or whatever.
But if you don't, you just change the expectation of the diarrhea to make it not to one, or whatever the value is.
So the expectation of individual values are the alphas divided by the sum of the alphas. So if all the alphas are 1, the expectation just becomes 1 over k. But the pies have a posterior distribution. So you can look at that as well. It's not easy to see in this plot, but they do have a posterior distribution. Okay. Also, BRMS makes it easy, like you don't usually have to make your own plots because it has this function called conditional effects that you can plot the output of it and you get something like this. So we restricted age to be monotonic. We did not restrict it to be linear, or like the categories to be like equally spaced or whatever. So although people 25 to 34 are a little bit less likely to support Obama than people 18 to 24, there's not a big difference here. Again, not surprising. But as you get into older ages, you get bigger steps down. And for people 65 plus, much less likely to support Obama than even people in those sort of 45 to 64 range. So we see the monotonic, but not linear, decreasing relationship that we've estimated here. And that can all be done with the conditional effects plot. Now, as we talked about before, in a generalized linear model, as opposed to a perfectly linear model, you can't really interpret one parameter in isolation of the other. So what conditional effects does, I believe, it sets all the other variables besides age to their average values, and then fixes those, and then shows how the probability of supporting Obama changes as age varies, holding all the other variables at their average. But you can and might want to set all the other variables to something different to then, visualize the effective age or whatnot. We can also do posterior predictive checks. So this doesn't look great. Too many. So this we've talked about before, but maybe not gone into much detail about it. So we have those Pareto K things that get estimated by Pareto smooth leave one out importance sampling. And if those were actually distributed Pareto, if you stick them into a Pareto CDF, you would get a uniformly distributed random variable back. That's what was reflected by these draws with the gray lines. When we actually do that in this case, we get the dark blue line, which looks not uniform. Too few small Pareto K values, too many big Pareto K values. So it's not predicting enough dispersion. Honestly, this is not awful. Like once you start checking your model, then you get this sense that like your model is terrible. But other people who don't check their model would be like, oh, this model is like actually working pretty good. But anyway, this could probably be improved, but you got to check to start. So now we're going to flip to thinking about the outcome variable as having ordinal categories. So if the outcome was what is your income range, and then gives you buckets where you can put income. Or another thing, not really social science, but the hurricane scale. We have like category 5, category 4, category 3, category 2, category 1. So actually those categories are entirely determined by the wind speed of the hurricane. And that is something that people have criticized about, because if you just think about the wind, of the hurricane that doesn't tell you how much rain is going to fall or how much the tide of the ocean is going to come into lower Manhattan or other things like that that can be extraordinarily destructive, even if the wind is not like enough to blow the
Or the
entire statement.
or the angle which it comes in.
Yeah, that too. So the hurricane classification is a very simple function of wind, which is continuous, but then they discretize it into category 1, category 2, category 5, whatever for television. So similar deal here. I think Y star is your like true income, but the survey doesn't really ask you for that level of detail. They just say, are you between like 30,000 and 50,000 or, you know, something like that. So what we observe, you can think of as an integer between 1 and J, if there are J possible income categories. And you say my income is 1 if your true income is less than the first cut point, C. You say income is 2 if your true income is between the first cut point and the second point, etc. And then you say up to J if your income is greater than whatever the last cut point of the buckets are. And then, you know, if we were doing a model like we were doing with the census data, we could say, you know, your true income is E to, you know, this, and model eta is being in log units with, you know, normal errors, usual linear predictor, normal priors, etc. So all we've really changed is the top part here, which maps the true underlying continuous Y star to ordinal categories. And this is an example of what is sometimes called interval censoring. What we did on the homework, we had like top coding censoring, and that was equivalent to like survival modeling censoring if the people that they're studying are like not dead yet, sort of deal. But interval censoring is something, and it happens in the social sciences actually kind of a lot, where we have this underlying continuous thing that we want to model, but we have this very crude measurement in buckets that the data come in. However, main thing to keep in mind here, the C's are known. They're in the survey. Like C1 is $30,000. So you're in bucket 1 if your income is less than 30,000. So the C's are known. They are not being drawn from any sort of a distribution. And so how will we draw from the prior predictive of, you know, something like that? This is all the same. Eta is, you know, the same after we cross-join it together. Let's say the X is already centered or whatever, so we can use gamma there. We draw the epsilons. We make the Y star, and then we have a cut function in R, which takes a continuous thing and cuts it into categories using our vector C as the breakpoints, saying like 10,000, 30,000, 100,000, whatever are the dividing lines that our hypothetical survey asked about. And so the Y that we observe is this integer between 1 and J. Right? So if that's the data generating process, what would be the log likelihood? So similar to what we saw last time when the people were top coded, we had to evaluate a CDF, or the logarithm of a CDF, to get the probability that someone was surviving longer than the end of the study or top coded or whatever. If like everything is in buckets, then the probability of the outcome Y, you know, falling in this or that bucket, or the bucket C indexed by Y minus 1 up to CY, is going to be the CDF for the cut point indexed by Y minus the CDF for the cut point indexed by Y minus 1, as we saw before. Difference of CDFs is the probability of falling between here and there. And that's going to vary as a function of eta, and that varies depending on the x's and the betas and the gamma and all that. So we just have to evaluate the logarithm of a difference of CDFs to get the probability of falling in each category, and then the sum of the logarithms gives us the log likelihood. And so we're not even going to do an example of that because interval censoring with known cut points it happens in the social sciences, but it's not super common. What is much more common is you have an ordinal variable like how much do you approve of Biden, and the survey gives you answer categories that are in a so-called Likert scale. Usually like a 5-point Likert scale will say strongly disapprove, disapprove, some way of saying neutral, I agree or support Biden, strongly support. And so that would be like a 5 category. Sometimes there'll be 3, sometimes there'll be 7. It's pretty much always an odd number, and then the one in the middle is some sort of expression of neutrality. But in a situation like this where you have like strongly disagree, disagree, neutrals, agree, strongly agree, then that differs from the previous one in that the cut points of this underlying continuous thing of like how much do you support the job that Biden has done as president are unknown. So instead of C's, I indicate them by zetas, and those are unknowns, and so they're going to have a prior distribution, and consequently when we condition on the data, they're going to have a posterior distribution. So it's the same observation mechanism mapping y star to y, but now the cut points are unknown random variables that we want to express our beliefs over. They have to be in increasing order. We do know that. But we don't know in advance what their numerical values are. So there's different sorts of priors you could put on the cut points. BRMS actually has a different default prior than stan_POLR in the rstan_arm package, which estimates the same model here. Another thing is that this model, if you're going to estimate all these cut points, you don't estimate an intercept. So there's no gamma or alpha here. You do have predictors, and they have coefficients, and the coefficients have priors, and you're going to have a prior on the cut points as well. But there is no intercept in this form of the model. So basically, the process to draw predictions is going to be similar basically to what we had before. It's just now we have additional unknowns with all these zetas that we're going to need priors over, and then we cut the underlying continuous thing, which we don't know, based on its relationship to the zetas into the observed y that we see. So an example of this that's used in the BRMS package has something to do with a data set on inhalers. So the outcome variable here is, I guess, the rating that people with asthma gave to their brand of, their prescription of inhaler. I don't know exactly how that was, but this was some sort of a randomized experiment where I guess people were given like a placebo inhaler or like a new sort of inhaler, and they were asked to rate the effectiveness of it, and it depended on this, to them unknown, whether they were treatment or control group. So we can get the priors that are used by default. So the log likelihood function for the model I was just talking about is called cumulative in BRMS. You can either have logistic or probit inverse link function, the CDF that is used for that. The default priors, as usual, are not good, particularly on the coefficients where they're improper. The BRMS regrettably calls the cut points intercept 1, 2, 3, which is not a good phrasing, but that's what BRMS does. Yes?
So what happens if you have like a categorical variable in this case, like maybe brand or something like that? Would you like convert it. Then, like I was just thinking, like brand might have an impact on this case.
So brand is a predictor?
Yeah.
Yeah. Okay, so you can have ordinal predictors of ordinal outcomes.
Oh, okay, it has to be ordinal.
And so you may, probably with brand, you wouldn't want to do this monotonic thing because,
Okay.
like, how would you order the brands? But you could have an ordinal predictor of an ordinal outcome, and that would just still do the regular stuff with the ordinal predictor. What we want to focus on here is the fact the outcome is ordinal, and consequently we have unknown cut points, which I called in the math zeta. BRMS refers to them as intercepts. Basically, all statisticians refer to them as cut points. So intercept was not a good choice of word, nor is the default prior a good choice of prior. It has way too much variability for those. But anyway, if you use like standard normal priors on the cut points and like zero centered priors on the betas, that'd be fine. Specify this model family is cumulative. You get back posterior distribution of stuff. So the posterior expectation of the treatment effect has a negative sign to it. I think lower values of rating corresponded to better approval of the inhaler. Yelp does it the opposite way. But anyway, so depending on how it's coded, that may or may not make sense. But anyway, we get posterior estimate. We can make plots, all this stuff. All sorts of things like that. Now, in one of these ordinal models, if the treatment like shifts the Y star over, that doesn't necessarily increase the chance that you fall in the category. So if the treatment effect is really big, it might mean so many people are falling in category 1 that the probability of falling in category 2 is actually lower. So you really have to make a plot to sort of visualize what's going on here, and that is facilitated by the conditional effects function. So we have the different colors for the 4 different ratings. And so, if you compare the same color to the same color, so if you're in placebo group, this is the probability of rating in the first category, the inhaler, versus if you're in the treatment group. And so that has clearly gone up. But for the 2 and or let's just say the 2, the probability that you rate in category 2 actually goes down. And that is not at all obvious from just looking at the table of posterior means and like credible intervals and stuff like that. You have to map it to the probabilities to sort of see. And the category 3, category 4 is so rare that it doesn't even really register that much in this plot. So anyway, this is yet another example. Outside of extremely linear models, no link function, anything like that, you can't just look at a coefficient in isolation and expect it to tell you everything you need to know, and sometimes it doesn't even tell you anything you need to know. But you have draws from the posterior distribution, and that's basically what BRMS is doing with this conditional effects stuff. Then you can push those through the inverse link function. You can get probabilities, and you can show how the probability of rating someone or the inhaler in category 1 changes depending on the level of a predictor, holding all the other predictors at their means, which is what the default does with conditional effects. So plot rather than guess based on them. So last thing for today, another model that is supported by BRMS. It's actually not included in RStanArm. So RStanArm, I could have estimated this model with using stan_polar. It has different priors, but the same likelihood function. or different default priors, same likelihood function. Yeah. But another model that BRMS supports, which RStanArm doesn't. Okay, so the model we were just talking about, particularly if you use a logit inverse link function, is called a proportional odds model. And that's because eta has the interpretation as the logarithm of the probability that you're greater than or equal to the J's category divided by the probability that you're less than the J's category. For all J, it should be for all J greater than 1. But in any event, and so if you only have 2 categories, this simplifies to the binary logit model that we've been talking about before. But the reason it's called proportional odds is that this interpretation holds for all J possible categories that we could talk about. But suppose instead of the outcome being like how much do you support the job that Joe Biden has been doing as president, what if the question was, what is your highest educational degree? So if you're interested in education, something like that. And so the probability that someone answers like, I'm a college graduate or I have a bachelor's degree or whatever, it's the probability they graduate from college and that they don't have a graduate degree, at least not yet. So there's actually 2 aspects to that answer that you need to have the probability of. And in the so-called stopping ratio or continuation models, the interpretation of eta changes to the logarithm that you're in category J divided by the probability that you're in category greater than J. And this can be more appropriate if you're thinking about outcomes for something like this, where the person has the opportunity to stop at like each level of education and say like, I don't want to get any more degrees or anything like that. And so you might say, well, how could I choose between those models? Well, you could choose on the basis of expected log predictive density, or whichever one makes more sense. So theoretically, if you just change the family to S ratio instead of cumulative, then you can get that posterior distribution. You get back different numbers. And so who's to say that this posterior distribution is better or worse than the posterior distribution we had previously? We can use Lu compare. And in this case, it actually says the difference is negligible. So you could go based on your understanding of inhalers as to whether the sort of cumulative proportional odds thing makes more sense, or this idea of, I could go this step, and then stop and not continue more steps, if that sort of makes sense. I guess in the case of inhalers, I would probably, inhaler ratings, I would probably say the cumulative model makes more sense, but could have gone either way. In fact, it just doesn't really matter that much for this data set, but in other data sets, it's fine. Okay, out of time. We'll have office hours recitation as usual next week, and we will start to get into hierarchical models, both with RStanArm and with BRMS, which is really where the differences between Bayesian approaches and non-Bayesian approaches start to get extremely stark. So that's important. Sure to check that out.